Welcome to the course on principles of vibration control. So, now we will be talking about linear viscoelastic materials and their models. So, we will be discussing about how to model a viscoelastic materials very specifically in this lecture. So, the things that we would like to cover is first of all a brief introduction to the viscoelastic materials, and then we will talk about the stress strain relationship of the viscoelastic material, and then we will propose certain models. For example, we will start with the linear elastic spring and then linear viscous dashpot, and something which will be derived out of these two by mixing these two, that is the Kelvin-Voight model and the Maxwell model. So, that is what is our learning goal today. Now, first of all, we will be giving a brief introduction to the viscoelastic materials. Here with me we have two viscoelastic materials. One of them is more lossy, that means it will behave in such a manner that it will dissipate more energy, and another is more elastic in nature. So, let us see, both of them are very much identical in terms of their shape and size, etc. But if we just drop one of them from a certain height, we can see that there is a ball like behavior, that means it is actually quite springy. That means when I am dropping it, it is not dissipating much of the energy, it is getting it stored, and that energy is helping it to bounce back, and this back and forth is happening for some time. On the other hand, imagine a material which has lot of loss associated in it, like this one. From the same height, if I drop it, you can see that there is almost no bouncing in the material. So, that would actually help us to do this conjecture that this material, even though they are very much identical in nature, at room temperature is actually more viscoelastic in comparison to the other material. And this viscoelasticness of the property of the material, in which we have two parts associated in it, one is the viscous part and another is the elastic part. The viscous part is actually more predominant in this material, which had shown very less amount of which has dissipated more energy, in the sense that which has shown very less amount of jumping phenomena in comparison to the other one. So, this with in a brief kind of an idea we will keep with us. So, a very brief introduction about the viscoelastic materials. First of all, these viscoelastic materials actually consist of polymers which has variable chain lengths, and some of them can be of short chain length, some of them can be of long chain lengths. In fact, you know that the polyethylene that we use most of the times, we divide it into two categories. One is called low density polyethylene or LDPE, and another is called high density polyethylene or HDPE. Now, low density polyethylene has actually short chain lengths and it has low molecular weight, and high density polyethylenes are having long chain lengths and it has high molecular weight. So, like that, in the same polymeric category itself you can have variable chain lengths in it, and the viscoelastic materials include natural and synthetic rubber like substances, which is more important for us from the vibration control point of view, such as butyl rubber, silicone rubber, polyurethanes, etc. And it is extensively used for controlling vibration because it has enormous resilience as well as high energy dissipation capacity. We have just seen shortly before that how high is the energy dissipation capacity, that just after the first bouncing it did not bounce back at all. So, that is what is the telltale sign of a good viscoelastic material. Now, where from this high damping capacity comes? It is generally attributed to the long chain molecules which actually provide internal frictions. So, imagine you have a long chain. So, suppose we consider a viscoelastic material of this type, quite a long chain. Now, what will happen? It will not remain straight. In between, sometimes there will be entanglements of it, and then the chain will continue. So, there are many such entanglements possible inside the system, like if it is a very long slender system. Now, naturally there will be internal frictions between these loops. So, the chain to chain internal frictions will take place, and not only that, these chains also may have lot of pendants in them, lot of atoms from the main structure, and then there will be degree of freedom of these things as well. So, they may start to actually dissipate energy like little pendulums which are fixed with the system, and hence they will also contribute in terms of energy dissipation. So, the very nature, the very structure of viscoelastic materials is always in favor of energy dissipation, and that is why they are of very good use to us for vibration control. However, there are some disadvantages of it. For example, viscoelastic materials are highly sensitive to loading rate, how fast I am actually loading a viscoelastic material, and what is the temperature at which I am working on the viscoelastic material. In general, we say that a very high loading rate is not very good to see the viscoelastic materials in action, and it is also true from the temperature point of view. A high temperature is also not very good to see the viscoelastic materials in action, neither a very low temperature. It is somewhere in between, we call it to be a glass transition temperature, where we see the best properties of the viscoelastic material. Now, in the stress strain curve, I have already earlier told you that actually the the elliptical form comes up in the which also depicts the area under the ellipse, also depicts the hysteresis or the energy that is lost per cycle. Now, this particular ellipse, the major axis of the ellipse is actually a measure of the material stiffness, while the ratio of the major to minor. So, if we know the major, we know that how much is this actually is the stiffness, but the ratio of the major to minor, which in some sense tells us that what is the ellipsoid nature, that would actually give us a measure of the damping of the material. Now, with this little background of viscoelastic materials, we would also like to see that how these viscoelastic materials behave with respect to temperature. Suppose I take this material called polystyrene, which shows very good viscoelastic properties close to room temperature. Now, this particular material or such types of viscoelastic materials actually shows 5 phases in terms of their physical nature. So, much unlike the metals, which may in the solid state itself in a metal or a metallic or a kind of a crystal will show at most 1 or 2 phases in it, or maybe there will be some changes in crystal structures which may be 2 or 3 times the change of crystal structure will happen. But here for this kind of viscoelastic materials, there are total changes in terms of the nature of the material itself. For example, for this polystyrene, if you keep it at a very low temperature, it will be like in a glassy region. So, this is the phase 1 or the glassy region, which will be here at a low temperature. At this point, you will see that the modulus of elasticity is relatively high, means what is going to come up at a later stage in comparison to that, the modulus of elasticity is relatively high, nearly close to we say that 2 gigapascal or so. It cannot be very high for polymeric materials, but close to that, and it is very hard. That is true. You take any such material and for example, simple polyethylene and then plastic sheet what you call, and keep it in the freeze, and then you will see that it would become very hard in the low temperature region. So, with respect to low temperature, this behavior also you will see, and it will have a high resistance to flow. So, that is your phase 1, and in fact, this happens because all the chains which gives this fantastic mobility to the viscoelastic materials, they remain frozen at a low temperature. So, that it does not really get an opportunity to show the viscoelastic behavior. Now, as the temperature is increasing, these frozen chains are becoming active. They would start to move against each other. So, this is where we will get this leathery or glass transition region, and this is marked by a sharp decrease in the elastic modulus, and this may also have deformation which will not be totally recoverable, like your elastic recovery may not take place, and that is what is this transition region or the leathery region. Now, there are several theories for this transition. Some people say that, let us imagine that this is the main chain of a viscoelastic material, then it can happen that this main chain, the part of the main chain will actually crank itself and will start to rotate with respect to some equilibrium condition, and thus gives a kind of a mobility in the system. There can be another mobility also, as I told you, that suppose if there is a a side chain from the main chain, then there can be mobility also in terms of the motion of the side chains. So, all these things basically contribute towards the sharp decline in terms of from glass transition region, and then we come to the region which is known as the rubbery region. In this region, both elastic and viscous components are present. Of course, viscous component will be more dominant now, and the modulus falling rate will be stabilized now, because almost all the links has become active. So, that will stabilize. Elastic behavior will come at a high strain rate, and viscous behavior will come at a low strain rate. So, that means at the rubbery state, if I apply the deformation at a very high rate, then it would not be able to follow it, and it will show a kind of a elastic behavior resisting that kind of a change. But if I do it slowly, it will follow it, and that is the viscous behavior at the low strain rate. So, this is what is our phase 3. Beyond that, the viscosity will start to dominate, because the temperature has increased now. So, the rubbery flow will start to take place. So, and the modulus will start to fall once again, and finally, when we are at phase 5, then we have the viscous flow region, and the modulus will drop very steeply. Basically, we will reach the fluidic region, and the melting point is somewhere here. So, for polystyrene less than 200 degrees centigrade itself, you will see this kind of a change. So, thus in a nutshell, once again we are going to see 5 regions of viscoelastic behavior. Very low temperature region 1, which is glassy. At that time the modulus of elasticity is high, and then the modulus of elasticity starts to decrease, that is the leathery or the transition region or glass transition region, and which happens because of, I told you that, the mobility of the chains, and the modulus of elasticity falls down significantly. After that, there is a kind of a stabilized region which is marked by the rubbery region, and then from the rubbery region once again the beyond a certain temperature the viscosity will start to dominate. So, we will be having a rubbery flow region, and from rubbery flow region, still in the rubbery flow region there will be some resistance to deformation. That means, there will be some kind of a elastic behavior, but beyond a certain temperature from the rubbery flow region we will come to the viscous flow region, where there will be only viscosity which will resist the deformation of the system. So, basically it will be proportional to the strain rate of deformation, and that is how we are going to get the 5 regions of viscoelastic behavior. Of course, finally, if you increase the temperature much for some of the materials, not for all, a decomposition can happen. That means, all these things will break down and the gases will come out of it. So, that can happen in some of the materials. Now, we come to the whole thing that we have said so far qualitatively, we come to a quantitative description of the fact. Now, naturally, if we want to say that, we have to say here that both the stress is proportional to the strain rate and from the another side also the strain is proportional to the rate of change of stress. So, what it means is that we have for example, the stress proportional to strain part, where A0 and B0 will come into picture, is typical of metals, but then beyond that also we have this stress rate or strain rate or rate of change of that or even higher order changes appears in the constitutive relationship of the system. Now, this particular thing we can actually sum it up in terms of a generalized Hooke's law, as you can see here, that we can keep the first term separate, A0 sigma plus I equals to 1 to n, we have the stress rate related terms here, and that equals to once again in the strain side first term separate. There is a reason I will show you, because it will be easier for us to understand B0 epsilon, and then for j equals to 1 to m we have the strain rate terms that will come into picture. In short, this is a law or extension of the Hooke's law, in which not only that stress is proportional to strain, but also many more intricate things will be kind of it will be expressed through this relationship, where stress and strain rates depending on the type of material will also play an important relationship. If all these coefficients A0 to An and B0 to Bn Bm if they remain constant, then we will call the material to be a linear viscoelastic material. For metals, for example, A1 to An is 0 and B1 to Bm is 0. So, what it means is that for metals A0 sigma equals to B0 epsilon. So, if I divide both the sides by A0, because A0 is just a constant, so sigma is B0 over A0 times epsilon, and I can write it as E times epsilon. So, that is how for a metallic case we do not get any other variation of rate of strains etc., but simply stress proportional to strain, which is our very simplified form of the Hooke's law. Whereas, in this case you get all these rates that will come into the picture. Now, we will talk about the testing of the viscoelastic materials. So, based on the stress strain relationships, we will show this testing of viscoelastic materials. Now, it involves loading a material either at constant stress and holding that stress for some length of time and then removing the load. That means, at a particular time I have started the load constant, it is not changing, holding it and then removing it. So, this is what we say as a creep recovery test. So, if we do this test on a viscoelastic material, what we will find is that as soon as I apply this stress, the strain will start, and then my stress is constant, but the strain will not stop. So, this is the instantaneous part of the strain. After that, my strain will start to show the secondary part or tertiary part, which is also known as the creep strain. So, if I keep the load fixed, or in other words the stress fixed, then we will first see the instantaneous strain followed by the creep strain that will happen to the system. What will happen if I remove the stress? Instantly some part of it will come down, and that is what we call it to be elastic recovery. There is some part of it which will not come down instantly, we are going to call it to be anelastic recovery, and there is some part of it which will not be recovered, that means it will not come down to 0 at all. So, this is the permanent strain that may be fixed inside the system. Such is the nature of a creep recovery test when we are subjected to the material to this kind of a stressing of the system. Now, let us look into the stress relaxation test, which is this stress recovery, or the creep and the stress relaxation are just two other types of the coin. Now, in case of these, we are going to strain a material at constant strain, not constant stress like the last time. So, here this is a epsilon versus T curve, where I am applying an instant strain and then holding it constant here. What you will see is that the stress required to hold the viscoelastic material the constant strain will actually decrease over time, and this phenomena is known as stress relaxation. So, you can see here, as I have applied the strain, I am getting some stress developed in the system, and then this stress is actually coming down slowly. It may not come totally to 0, but it will come down constantly, and this is what is known as the stress relaxation in the system. Now, let us look into some of the models that these are basically mechanical models. We also call them to be rheological model that we actually use in terms of describing the behavior of the system, and also these models are some of the very simple form of the generic Hooke's law that we had discussed for standard linear solid. So, the first model towards this direction is the linear elastic spring model. So, in this case we have a spring here, it is a linear and a elastic spring, and I am applying stress to it, and I am getting instantaneous strain into the system. So, the response of this material to a creep recovery test, let us say, to undergo an instantaneous elastic strain upon loading, to maintain that strain so long as the load is applied, and then to undergo an instantaneous destraining upon removal of the load. So, if you look at it, that here we are applying the stress, and then I am getting an instantaneous strain. So, this is the load or the stress, this is the strain. So, we are getting some instantaneous strain. We are holding the load here, we are having the strain also to be constant, because this is spring, this is not showing any viscosity, and then I am removing the load. At that same time TR, time of relaxation, the strain also will come down and it will come to the base state. So, that is how an elastic spring should behave, and that means I can depict it by a very simple relationship where the stress is proportional to strain, epsilon is sigma over E, we also call it as S times sigma, where S is also known as the compliance modulus of the system. So, this is your very much simplified Hooke's law that a spring shows. Now, if I go from this to a viscous dashpot, how the scenario is going to get changed? Well, I told you earlier that a dashpot is a piston cylinder arrangement, as you can see here, this is a piston cylinder arrangement, and which is filled up with some kind of a viscous fluid. We have not shown it here because that is just a symbol, but this is the way you can consider that the dashpot is filled up. Now, a strain is achieved by dragging the piston through the fluid. This we can easily understand, that if I try to pull it this way, it will come out, and that means a strain will be achieved. So, if I subject this to a test of something like that, I am applying a stress to the system, keeping the stress fixed for some time, then removing the stress and bringing it to 0. How will this fellow behave? Well, at the very first instant when I have applied the stress, I want the dashpot to move. But have you ever seen a door closer which you can instantly close the door? You cannot. So, that it is the very same thing, you apply the stress, but the strain is 0 initially. That means the dashpot will refuse to move at the very first instant, because it takes some time for these molecules to rearrange themselves. So, that refusal will come, and then gradually it will give up. So, gradually you will see that the strain is happening in the system, and it will come to a point of maximum strain when I am having this stress constant. Beyond that point, even if I remove the stress, the deformation is going to stay there. Why? Because there is no springiness in the system, there is nothing through which the system will recover itself back. Now, naturally, as you can see here, that in this particular region, it is actually the strain rate which is actually constant, and hence we can actually express it with respect to this kind of a formulation, that the stress is proportional to the strain rate. So, that means epsilon dot rate of change of strain with respect to time, that equals to sigma eta, where eta is not actually the loss factor here. You have to keep in mind there is some kind of a damping coefficient or viscosity of the material. So, epsilon equals to, so if epsilon dot equals to sigma over eta, what happens if I integrate it? I will get it as epsilon equals to sigma over eta t plus some constant. Now, if I assume 0 initial strain condition, that means that t equals to 0, t equals to 0, if I assume there was no pre-strain in the system, that means this constant will be 0. So, that means with respect to strain, the relationship would look like epsilon equals to sigma 0 over eta times t. So, the strain is seen to increase linearly, that is what we have seen here, that with respect to the strain temperature behavior, strain is increasing linearly. So, that the slope of this curve is actually sigma 0 over eta. So, that is how it is going to behave. And when the load is removed, there is no stress to move the piston back. So, the piston will actually remain at that state and the strain built up will be permanent. So, that is what is our linear viscous dashpot model. Now, what if I mix the two? That means, what if I make a Kelvin-Voight? There are two ways in which I can mix the spring and the dashpot. One is that a spring and a dashpot, as has been shown here as parallel, and another possibility is that the spring here and the dashpot is in the same line itself. So, this is a parallel circuit and this is a series circuit. So, I can build up these two models. Now, we have to see that what is the kind of implication of building up these two models. So, in the first case then the spring part sigma 1 is E epsilon 1 and stress in the second part, in this part, is sigma 2 as eta d epsilon 2 dt. Now, because it is a parallel combination, that means whatever suffering or whatever good thing or bad thing that is going to happen, it has to happen together. So, that means the strain that it will be subjected to from both the sides, it is same both for the spring as well as for the dashpot. So, epsilon is epsilon 1 equals to epsilon 2. On the other hand, the load is actually shared by both of them. So, if I try to pull it, then the resistance, there will be some resistance here, some here, it will be shared by both of them. So, that means the stress is actually partly the stress in the spring and partly the stress in the damper. So, I already know that sigma 1 is proportional to strain. So, E epsilon and sigma 2 is proportional to strain rate. So, it is eta d epsilon dt. So, if I compare that with my A0 to AN model and B0 to BM model of a standard linear solid model, you will see that this implies that for this model A0 has to be unity, B0 has to be E only, A1 is to be 0 and B1 is to be eta. So, if you put all those things, A0 as 1, so that means it is 1 times sigma plus A1 is 0. So, that second term does not come into picture at all, that equals to B0 is E. So, it is E times epsilon plus B1 is eta, which is the damping coefficient. So, eta times d epsilon dt, and we are going to get back the same equation here. So, it is a special case of the generic Hooke's model where these are the parametric values of the system. So, that is what is our Kelvin-Voight mechanical model of the system. Now, if I look at the response of that Kelvin-Voight model, there are two responses that I will discuss today. One is if a load sigma 0 is applied suddenly to the Kelvin-Voight model, and then what will happen? Then the spring will want to stretch, but it cannot stretch because the dashpot is there. Whatever has to happen, I told you in a parallel model, has to happen together. So, since the dashpot will not allow it to get strain, so that means the dashpot will take the load. So, that means in the very first part, the creep curve will start with an initial slope of sigma 0 over eta, because this is where the dashpot will first be prominent, it will come into picture. Now, as some strain will be occurring to the system. So, that is your sigma 0 over eta part, some strain is occurring to this system, and then what will happen, some stress will be then transferred from the dashpot to the spring. The spring will have now some space to deform. So, now the spring can actually squeeze because the dashpot has moved forward. So, that squeeze will take place, and then that means that the second part of the stress will now start to show its effect. So, this will have the sigma 2 part that will come into the picture of the system, and so sigma 1 part will come into the picture, and sigma 2, the dashpot part, will be actually ever decreasing. On the other hand, the sigma 1 part will become gradually sigma 0 over E. So, that is what is happening here, that the spring has taken the domination, and that is why if I remove the stress, then the spring starts to show the initial deformation, and then the rest of the deformations gradually it is coming down to 0. So, this part is actually dashpot dominated initially, and this part is actually spring dominated. So, thus in the creep recovery response we get the manifestation of both the properties of the system. So, we have the relationship, that is E epsilon plus eta times d epsilon dt. Now, if I try to solve this with an initial condition that there is no pre-strain in the system, you will see that at any point of time you will get epsilon, which is be depicted by this kind of a relationship where there is sigma 0 over E, and then there is an exponential part 1 minus e to the power minus E by eta t, which you can write it as sigma 0 times j t, and j t is known as the creep compliance function, which is 1 over E 1 minus e to the power minus E by eta t. You can even write it as the ratio of the time, so time of relaxation, where T r is the eta over E, and this is also known as the retardation time for creep strain to accumulate. So, when the KV model is actually unloaded, the spring will want to contract, but again the dashpot will hold it back. The spring will, however, eventually pull the dashpot back to its original 0 position, and full recovery will start to occur. So, there is a transient type creep and inelastic recovery in the system, but no instantaneous or permanent strain in the system. So, this is what is the Kelvin-Voight model system. And if you look at the stress relaxation in the Kelvin-Voight model, then in this case you are subjecting the material to a constant strain, that means epsilon 0 at t equals to 0, the the constant strain is coming to picture. So, d epsilon dt is 0, and then you get the relationship as sigma equals to E epsilon 0. From this relationship, if I put d epsilon dt to be 0, this term vanishes, and this shows sigma equals to E epsilon 0. Thus, the stress is taken up by the spring and is constant. So, there is, in fact, it shows according to this model that there is no stress relaxation over time, but actually this Kelvin-Voight model undergoes an instantaneous strain of epsilon, and an infinite stress needs to be applied to do this. So, in practice this would never happen, because in order to show an instantaneous strain, like this relationship shows that an instantaneous deformation is possible in the system, this is only possible if infinite stress is applied to the system, otherwise this will not happen. And hence we can say that the model is good with modeling creep, which we have shown in the last part of it, that this is good, but it is not good in terms of showing the instantaneous strain. So, with regards to relaxation, the model is much less accurate, and its application is in organic polymers, in rubber, woods, when the load is not too high. So, this is where we will put an end to this lecture, because here we have only talked about Kelvin-Voight model. In the next lecture we will talk about the Maxwell model.